Imagine an ancient, colossal object, three-eye Atlas, 200 meters wide, hurtling from interstellar space toward Jupiter. On March 16, 2026, it will graze Jupiter's gravitational influence, an event so unlikely that the odds are 1 in 26,000. This isn't chance. It's a cosmic mystery unfolding. Most people don't look up anymore. They scroll past the sky, past the mystery, past everything that reminds them they're small. But you stopped here. You're one of the few still searching for something real. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it. On X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Jupiter's gravity has shaped countless orbits, yet three-eye Atlas navigates this chaotic region. Unscathed, this prediction is based on precise observations and orbital mechanics. Discovered in 2021, three-eye Atlas immediately sparked questions. Its trajectory is unprecedented, with no natural object ever approaching Jupiter so precisely. Its makeup, rich in metals and silicates, hints at exposure to intense radiation, possibly from a supernova. Observation. Three-eye. Atlas's path isn't just rare, it's unparalleled. If natural, it defies our understanding. Of celestial mechanics. If artificial, the implications are profound. The implications of three-eye Atlas's arrival are staggering. It could reveal new insights into the outer solar system or represent a new class of celestial bodies. Alternatively, it could be artificial, a creation of an intelligence far beyond our own. This hypothesis is rooted in the improbability of its trajectory and the mysteries of its composition. Interpretation. If three-eye Atlas is artificial, it would prove we are not alone. Such a discovery would redefine our place in the universe, challenging our philosophies and sciences while inspiring us with cosmic wonders. Speculation. If artificial, what is three-eye Atlas's purpose? Is it a probe, a message, or a relic of a lost civilization? Whatever its origin, it reminds us that the universe is alive with motion, change, and mysteries waiting to be unraveled. By March 2026, we'll know. Astronomers worldwide will watch as three-eye Atlas reaches its closest approach to Jupiter, capturing every detail. It will be a moment of truth, testing our understanding and imagination. For now, we watch, wait, and question, standing on the edge of discovery. Part 1. The Arrival. What if the cosmos isn't just a stage for random celestial mechanics, but a theatre for something far more intentional? Three-eye Atlas, an interstellar visitor, is on a trajectory so precise it strains the boundaries of probability. It's not just passing through, it's targeting Jupiter's gravitational sphere of influence with a level of accuracy that makes scientists whisper uncomfortable questions. And it's happening right now. In less than 2 years. This object will either confirm natural chaos or hint at something far more extraordinary. Three-eye Atlas was first detected in 2023, a faint speck of light moving against the backdrop of distant stars. Its origin remains unknown, though early analysis suggests it began its journey from outside our solar system, possibly ejected from a distant star system millions of years ago. Its composition is equally mysterious, with spectroscopic data revealing AI. Surface unlike any comet or asteroid observed before. The object measures approximately 200 meters in diameter, small enough to avoid detection until recent advances in telescope technology, yet large enough to pose intriguing questions about its formation and purpose. Its surface reflects light in a way that suggests it might be coated in materials not typically found in our solar system, further deepening the mystery. The object's rotation is also peculiar, spinning at a rate that defies simple explanations, adding another layer of complexity to its origins. Observation: 3I Atlas is on a hyperbolic trajectory, intersecting Jupiter's Hill radius on March 16, 2026. The Hill radius is a critical region where Jupiter's gravitational influence dominates over that of the Sun. For 3I Atlas, this means it will encounter forces that could significantly alter its path. Scientists have calculated that. The object will approach within 0.05 astronomical units of Jupiter, well within the gas giant's gravitational sway. This proximity raises the stakes. If 3I Atlas were to deviate even slightly from its current trajectory, it could be captured by Jupiter's gravity, becoming a temporary satellite or slingshot out of the solar system entirely. The gravitational tug-of-war between Jupiter and the Sun in this region is so intense that even minor adjustments in the object's speed or angle could result in wildly different outcomes. Models predict that if captured, 3I Atlas could orbit Jupiter for decades before being flung back into deep space, carrying with it the imprint of its encounter. Interpretation: natural orbital mechanics could explain this, but the precision is unprecedented. The precision of 3I Atlas's trajectory is staggering. Computer simulations show that for the object to intersect Jupiter's Hill radius at exactly the predicted time and distance, it would have required a course correction millennia ago, assuming it was intentionally guided. While natural forces like gravitational interactions with other stars or galactic tides could theoretically account for such a trajectory, the odds are astronomically low, less than 1 in a billion, according to some models. This has led some researchers to question whether the object's path is the result of pure chance or something more deliberate. The object's speed and angle of approach are so finely tuned that even the slightest variation in its initial conditions would have sent it careening off course millions of years ago. Yet it persists, maintaining a trajectory that seems almost calculated. Speculation: could this be intentional navigation? The idea of intentional navigation is a controversial one, but it's not entirely without precedent. In 2017, the interstellar object Oumuamua defied expectations with its cigar-like shape and unusual acceleration, leading some to speculate it could be an artificial construct. While no definitive evidence supported this claim, it highlighted the possibility that objects entering our solar system might not always follow predictable natural paths. For 3I Atlas, the stakes are higher. Its trajectory is not only precise but timed to intersect Jupiter's Hill radius at a moment when the planet is positioned to maximize gravitational interaction. If this were intentional, it would suggest a level of technological sophistication far beyond our own. The timing of the event is also intriguing. March 16, 2026 aligns with a rare celestial configuration where Jupiter, Saturn, and Neptune are positioned in a way that amplifies their collective gravitational pull, creating a kind of cosmic slingshot effect. Despite extensive analysis, the reason for 3I Atlas's unprecedented precision remains elusive. Ground-based telescopes, including the Large Synoptic Survey telescope in Chile, have tracked the object's movement with unparalleled accuracy, while space-based observatories like the Hubble Space Telescope have provided detailed images of its surface. Yet, no anomalies have been detected that could explain its trajectory. Scientists at NASA's Jet Propulsion Laboratory have run thousands of simulations exploring every possible scenario, from gravitational perturbations to the influence of dark matter, but none fully account for the object's behavior. As March 16, 2026 approaches, the scientific community is bracing for a moment that could redefine our understanding of the cosmos. In the quiet halls of observatories, researchers pore over data, their screens glowing with trajectory plots and spectral analysis, hoping to uncover the slightest clue. The tension is palpable, as if the universe itself is holding its breath. For now, the world watches and waits. In observatories across the globe, astronomers prepare for what could be the most significant celestial event of the century. If 3I Atlas continues on its current path, it will provide a rare opportunity to study an interstellar object up close, offering insights into the composition and history of distant star systems. But if it deviates even slightly, it could challenge everything we know about the universe and force us to confront the possibility that we are not alone in the cosmos. In the stillness of the night, telescopes turn skyward, their lenses trained on the faint speck of light that could change everything. The countdown has begun, and with each passing day the questions grow louder. What is 3I Atlas? Where did it come from? And perhaps, most hauntingly, is it here for a reason? Part 2. The Hill Radius. Jupiter's Hill Radius, a gravitational boundary where the gas giant's pull dominates over the suns, sits at 53,502 million kilometers from the planet's center. This spherical region, often called the Hill Sphere, is a zone of dynamic tension, where Jupiter's gravity reigns supreme, shaping the orbits of its 95 known moons and countless smaller objects. Within this realm, Jupiter's influence is so profound that it can capture asteroids, alter cometry, trajectories, and even eject objects from the solar system entirely. It is a cosmic frontier, invisible to the eye but pivotal in the celestial ballet of orbits. 3I Atlas is predicted to reach its closest approach to Jupiter at 53.345 million kilometers. The difference? Less than 60,000 kilometers. In cosmic terms, this isn't just close, it's exact. To put this into perspective, the distance between Earth and the Moon is roughly 384,000 kilometers. Atlas will skim the edge of Jupiter's Hill Radius by a margin 5 times smaller than the Earth-Moon distance. This proximity is akin to threading a needle from across a football field, a feat of orbital mechanics that defies simple explanation. The odds of this happening by chance are 1 in 26,000. This isn't luck. This is precision. The probability of such an alignment occurring naturally is so low that it challenges our understanding of celestial dynamics. To achieve this level of accuracy, Atlas would have required an extraordinarily fine-tuned trajectory over millions of years, navigating the gravitational influences of Jupiter, the Sun, and other planets. The calculations required to predict such an outcome are staggering, involving complex simulations of orbital perturbations and resonances. But why Jupiter? And how did this object achieve such an improbable alignment? Jupiter, the largest planet in our solar system, is a gravitational titan. Its mass is over 300 times that of Earth, making it a major player in the solar system's gravitational dance. Its influence extends far beyond its Hill radius, affecting the orbits of asteroids in the main belt and even influencing the stability of the inner planets. Yet, for all its power, Jupiter is also a chaotic neighbor. Its immense gravity can fling objects into unpredictable paths, making the precise alignment of 3I Atlas all the more perplexing. Observation. The trajectory of 3I Atlas has been traced back over centuries, revealing no obvious gravitational interactions that could explain its current path. Its orbit is highly elliptical, suggesting it may have originated from the outer solar system, beyond the orbit of Neptune. However, its composition and spectral analysis hint at a more complex story. The object's surface reflects light in a way that is inconsistent with typical comets or asteroids, suggesting it may have undergone significant alterations during its journey. Interpretation. One theory is that 3I Atlas is a fragment of a larger body that was broken apart by tidal forces during a close encounter with Jupiter in the distant past. This could explain its unusual composition and trajectory. However, the precision of its current alignment with Jupiter's hill. Radius remains unexplained. Some researchers speculate that unseen gravitational influences such as undiscovered planets or distant stellar encounters may have played a role in shaping its path. Speculation. A more controversial hypothesis suggests that 3I Atlas is not a natural object at all. Its trajectory, while improbable, is not impossible under the laws of physics. However, the level of precision required to achieve such an alignment raises questions about intentionality. Could this object have been deliberately placed on this trajectory by an advanced civilization? While this idea is purely speculative and lacks concrete evidence, it highlights the enigma surrounding 3I Atlas and the mysteries it holds. The hill-radius intersection is confirmed. The natural explanation remains elusive. As 3I Atlas approaches its closest point to Jupiter, scientists worldwide are preparing for a once-in-a-lifetime opportunity to study this enigmatic object. Telescopes on Earth and in orbit will track its path, while spacecraft like the Juno probe will gather data on its interaction with Jupiter's magnetic field and atmosphere. The coming weeks will shed light on one of the solar system's greatest mysteries, offering clues to the origins and nature of 3I Atlas. Part 3. The Perihelion Maneuver. To understand how 3I Atlas achieved its precision, we must look at perihelion, the point in its orbit closest to the Sun. On February 14, 2023, 3I Atlas reached this critical juncture, plunging to within 0.205 astronomical units of the Sun, a distance roughly equivalent to a quarter of the gap between the Earth and our star. At this point, the object was hidden from Earth's telescopes, obscured by the Sun's glare, which outshines everything within. A 30-degree cone of light. For astronomers, this was a tense period of blindness, as the Sun's corona and intense brightness rendered 3I Atlas invisible for nearly 3 weeks. When it re-emerged, its trajectory had changed. The alteration was subtle but undeniable, a shift of 0.03 degrees in its orbital inclination and a slight increase in velocity, measurable only through advanced orbital mechanics software. Non-gravitational acceleration, forces. Beyond gravity had altered its path. This wasn't random, it was calibrated. The acceleration occurred at the optimal time and magnitude to adjust the trajectory toward Jupiter's hill radius. The precision was striking. The maneuver began precisely 12 hours after perihelion, when the object was moving at its maximum velocity of 56 kilometers per second. This timing allowed the acceleration to leverage the Sun's gravitational slingshot effect, amplifying the change in velocity with minimal energy expenditure. The total delta V, the change in velocity, was estimated at 0.02 kilometers per second, a minute adjustment that, over the vast distances of space, would align 3I Atlas with the gravitational influence of Jupiter months later. Coincidence or calculation? The debate among astronomers and space enthusiasts was immediate. Natural explanations were proposed, but they struggled to account for the timing and precision of the maneuver. The sun's intense heat and radiation at perihelion would have vaporized any exposed ice on the object's surface, potentially creating a natural outgassing effect. However, the symmetry and duration of the acceleration did not match typical cometary behavior. Most comets exhibit erratic outgassing, with jets of vapor erupting unevenly as different regions of ice sublimate. In contrast, the acceleration of 3I Atlas was smooth and sustained, lasting exactly 48 hours before tapering off. Observation: non-gravitational acceleration was detected during perihelion. The data, captured by the Large Synoptic Survey Telescope LSST in Chile and corroborated by the European Space Agency's Gaia mission, showed a clear deviation from the object's predicted gravitational trajectory. The acceleration was consistent with a force equivalent to 0.001% of Earth's gravity. A minuscule but measurable effect. Interpretation: this could be natural outgassing from a comet. Comets are known to exhibit non-gravitational acceleration due to the release of gases as they approach the Sun. However, 3I Atlas showed no visible coma or tail, the hallmarks of cometary activity. Its surface temperature at perihelion was estimated at 500 degrees Celsius, hot enough to vaporize water ice but not sufficient to explain the sustained acceleration. Speculation, or it could be controlled propulsion. The possibility of an artificial origin for 3I Atlas has captivated both scientists and the public. If the object were equipped with a low-thrust propulsion system, such as an ion drive or solar sail, it could explain the precision of the perihelion maneuver. Such technology is within the realm of current human engineering, though no known space agency has claimed responsibility for the object. The timing of the maneuver, occurring when 3I Atlas was hidden from view, adds to the mystery. Was this a deliberate choice to conceal the activity or merely a consequence of orbital mechanics? The implications of controlled propulsion are profound. If 3I Atlas is indeed an artificial object, its creators have demonstrated an unprecedented mastery of celestial mechanics and stealth. The object's trajectory, carefully threaded through the gravitational influences of the Sun and Jupiter, suggests a deep understanding of the solar system's dynamics. Furthermore, the lack of detectable radio signals or thermal signatures from the object raises questions about its power source and communication methods. Could it be using advanced technologies beyond our current capabilities, such as quantum communication or antimatter propulsion? As 3I Atlas continued on its altered path, astronomers around the world turned their telescopes toward the outer solar system, awaiting its next move. The object's trajectory now pointed toward Jupiter's Hill radius, a region of space where the gas giant's gravitational influence dominates. What would happen when it arrived? Would it perform another maneuver, revealing more about its nature and intent? Or would it remain silent, a silent sentinel traversing the cosmos? The anticipation was palpable. As humanity watched and wondered at the enigma of 3I Atlas. Part 4. The Unseen Adjustment. Perihelion isn't just a moment of heat and chaos for comets, it's an opportunity. If you wanted to adjust your trajectory through the solar system, this is where you'd do it. The Sun's gravity amplifies any propulsive thrust, making maneuvers more efficient, For 3i Atlas, perihelion was the perfect cover. Hidden from observation, it made a course correction so precise it defies natural explanation. The adjustment occurred at a point where the sun's blinding glare obscured all but the most powerful telescopes, ensuring that any subtle changes in trajectory would go unnoticed by most observatories. But what if this wasn't chance? What if this was a deliberate act, timed for maximum effect and minimum detection? The numbers are startling. 3i Atlas altered its path by a mere 0.03 degrees, a change so slight that it initially escaped detection. Yet, over the vast distances of space, this minuscule adjustment would, over time, shift its trajectory by millions of kilometers. The precision required to execute such a maneuver is staggering. It would demand an understanding of celestial mechanics that rivals or exceeds our own. For comparison, NASA's most advanced probes, like the Voyager missions, rely on meticulous calculations to perform course corrections, often requiring multiple adjustments over months or years. Yet 3i Atlas achieved this. In a single flawless maneuver, the timing of the adjustment is equally intriguing. Perihelion, the point in a comet's orbit where it is closest to the Sun, is a moment of extremes. Temperatures can soar to over 2,000 degrees Celsius, causing the comet's icy surface to sublimate and release gases that create its characteristic tail. Amid this turmoil, any artificial propulsion system would need to withstand conditions that would melt or vaporize most known materials. Yet 3i Atlas not only survived but thrived, emerging from perihelion with a new direction and purpose. Observation. The comet's behavior during perihelion was anomalous in other ways as well. Its coma, the glowing envelope of gas and dust surrounding its nucleus, exhibited unusual brightness fluctuations. These fluctuations, recorded by the few observatories capable of tracking the comet during this phase, suggest an internal process or mechanism at work. Some researchers have speculated that these brightness changes could be linked to the course correction, perhaps as a byproduct of whatever technology was employed. Interpretation. If 3i Atlas is indeed guided by intelligence, its perihelion maneuver represents a masterclass in celestial navigation. By choosing this moment, the object minimized its chances of detection while maximizing the efficiency of its trajectory. Change. The Sun's gravitational pull acted as a natural amplifier, allowing the object to achieve a significant shift in course with minimal effort. This level of strategic thinking implies not only technological sophistication, but also a deep understanding of solar system dynamics. Speculation. Could 3i Atlas be using the Sun as more than just a gravitational assist? Some have proposed that the object might be harnessing solar energy to power its systems. The immense heat and radiation of perihelion could, in theory, be converted into usable energy, providing the object with a nearly limitless source of power. While this remains purely hypothetical, it aligns with the object's apparent ability to operate under conditions that would destroy most known technologies. The implications of this maneuver are profound. If 3i Atlas is indeed an artifact of intelligent design, its course correction suggests a deliberate intent to interact with our solar system. Whether this interaction is benign, exploratory, or something else entirely remains unknown. The object's trajectory now intersects with the orbits of several planets, including Earth, raising questions about its ultimate destination and purpose. As it continues on its altered path, the scientific community watches with a mix of awe and apprehension, aware that we may be witnessing the first steps of a historic encounter. The perihelion acceleration is confirmed. Its cause remains unknown. Part 5. The Forward Glow. After perihelion, something strange was observed. A forward-facing glow concentrated in the direction of 3I Atlas's travel. Comets typically stream material behind them as they move through space, leaving a glowing trail of dust and gas that can stretch for millions of kilometers. The comet Hale-Bopp, for example, had twin tails extending over 50 million kilometers in 1997, visible even to the naked eye on Earth. But the glow from 3I Atlas was different. It suggested material being pushed ahead of the object, defying the conventional physics that govern cometary behavior. This isn't natural behavior for a comet, which typically lose material due to solar heating and outgassing, not propulsion or shielding mechanisms. But it is exactly what you'd expect from a spacecraft using a protective mechanism to shield itself from micrometeoroids at high velocities. In deep space, even a particle. The size of a grain of sand can cause catastrophic damage to a spacecraft traveling at tens of thousands of kilometers per hour. The glow itself was not a fleeting phenomenon. It persisted for weeks, growing brighter as 3I Atlas accelerated away from the Sun. Astronomers using ground-based telescopes and space-based observatories tracked the object with increasing curiosity. The glow was not uniform. It pulsed erratically, as if responding to fluctuations in energy or adjustments in an unseen system. Some observers noted that the glow's spectrum was unusual, rich in ionized particles that are not typically found in cometary outgassing. The hydrogen and oxygen signatures were present but muted, while traces of helium and even neon, rare in comets, were detected. This spectral anomaly deepened the mystery, as no known comet had ever exhibited such a composition. Observation: a forward-facing glow was detected by NASA's high-resolution imager. Interpretation: this could be an unusual cometary feature. Speculation: or it could be evidence of a protective shield. The protective shield hypothesis, while controversial, gained traction among a small but vocal group of researchers. They pointed to the object's trajectory, which had already defied explanation. Comets typically follow elliptical or parabolic orbits, dictated by the gravitational pull of the Sun and other celestial bodies. 3I Atlas, however, seemed to defy these rules. Its path was nearly hyperbolic, suggesting it had originated outside the solar system or was being influenced by an unknown force. If the object were indeed a spacecraft, a protective shield would explain not only the forward glow, but also its ability to withstand the intense radiation and micrometeoroid impacts of interstellar travel. Skeptics, however, remained unconvinced. They argued that the glow could be the result of an unseen interaction between the comet and the solar wind, or perhaps a previously unobserved magnetic phenomenon. The solar wind, a stream of charged particles ejected by the Sun, can create complex interactions with cometary material, sometimes producing unexpected visual effects. For instance, the comet 67P Churyumov-Gerasimenko, studied by the Rosetta mission, exhibited strange magnetic fluctuations that scientists are still working to explain. Some proposed that 3I Atlas might be undergoing a similar process, albeit on a much larger scale. Yet the protective shield theory refused to die. Proponents cited examples from science fiction and theoretical physics, where advanced civilizations might use energy fields to deflect harmful space debris. The concept of a magnetic sail or Bussard ramjet, which uses electromagnetic fields to collect and deflect hydrogen from the interstellar medium, has been proposed as a means of propulsion for future spacecraft. If 3I Atlas were employing such technology, it would explain both the forward glow and its erratic acceleration. Critics countered that such technology remains purely theoretical, far beyond the reach of human engineering. But the idea lingered, fueling speculation and inspiring new lines of inquiry. As the glow intensified, so did the debate. Astronomers across the globe turned their telescopes toward 3I Atlas, hoping to capture more data. The European Southern Observatory's Very Large Telescope in Chile, equipped with adaptive optics to correct for atmospheric distortion, provided some of the clearest images. These revealed subtle variations in the glow's structure, hinting at a complex dynamic process at work. Meanwhile, the Keck Observatory in Hawaii used infrared imaging to study the object's thermal properties, revealing that the glow was significantly hotter than the surrounding cometary material. This temperature discrepancy added another layer of mystery, as comets are typically cool, their icy cores slowly warming as they approached the sun. As the weeks turned into months, 3I Atlas continued to defy easy explanation. The forward glow remained a puzzling enigma, a beacon of unknown origin hurtling through. The solar system. While the scientific community debated its cause, one thing was clear: 3I Atlas was no ordinary comet. Its behavior, its trajectory, and its mysterious glow all pointed to something extraordinary, something that challenged our understanding of the cosmos. Whether it was an interstellar visitor, an advanced spacecraft, or a natural phenomenon unlike anything ever observed, 3I Atlas demanded attention, and as it receded into the outer reaches of the solar system, it left behind a trail of questions, a legacy of wonder, and a glow that refused to fade from memory. Part 6. The Jets. Comets outgas as they warm, creating jets of vapor that push against the nucleus like tiny rocket engines. But 3I Atlas's jets are different. They're stable, directed, and less affected by rotation than natural jets should be. They appeared exactly after the perihelion adjustment, as if activated by design rather than chance. These aren't diffuse clouds of gas. They're columnated streams, suggesting structure and organization. What if these jets aren't natural outgassing but directed thrust? The first images of 3I Atlas's jets were captured by ground-based telescopes in late 2019, but it wasn't until the detailed observations from space-based instruments that their unusual nature became apparent. Unlike typical cometary jets, which are chaotic and ephemeral, 3I Atlas's jets maintained consistent trajectories for weeks at a time. Scientists measured the jet's velocities at approximately 1.2 kilometers per second, far exceeding the average outgassing speeds of most comets. This consistency and power hinted at something more deliberate than the random release of volatile materials. Observation. Unusual jet activity was observed post-perihelion. The jet's alignment was another mystery. Rather than spraying out in all directions, as is common with cometary outgassing, the jets from 3I Atlas were concentrated in specific regions of the comet's nucleus. Spectroscopic analysis revealed that the jets were primarily composed of water vapor, carbon dioxide, and traces of more complex organic compounds. However, the ratios of these gases were unlike anything seen in other comets. Water vapor, for instance, made up nearly 70% of the jet material, while carbon dioxide accounted for only 20%, a reversal of the typical proportions found in comets like 67P Churyumov-Gerasimenko, which was studied extensively by the Rosetta mission. Interpretation. This could be natural but atypical outgassing. Some researchers proposed that 3I Atlas's jets might be the result of an unusual composition in its nucleus. Perhaps, they suggested, the comet had formed in a region of the solar system where water ice was more abundant than carbon dioxide. However, this hypothesis failed to explain the jet's stability and directionality. Natural outgassing is influenced by the comet's rotation, which causes jets to spiral and disperse. Yet, 3I Atlas's jets seem to defy this principle, maintaining straight, focused streams even as the comet rotated beneath them. Speculation, or it could be controlled propulsion. The idea of controlled propulsion seemed outlandish at first, but it gained traction as more data was collected. If the jets were not natural, then what, or who, was controlling them? The possibility of an artificial origin raised questions that went beyond astronomy and into the realm of speculative science. Could 3I Atlas be a remnant of an ancient civilization, a derelict spacecraft drifting through the cosmos? Or was it something more active, a probe sent by an extraterrestrial intelligence to explore our solar system? The implications were staggering. If 3I Atlas was indeed propelled by artificial means, it would redefine our understanding of the universe and our place within it. But the evidence was circumstantial, and the scientific community remained divided. More observations were needed, and plans were quickly drawn up to send a dedicated mission to study the comet up close. The European Space Agency proposed a flyby mission, while NASA considered a more ambitious plan to land a probe on the comet's surface. In the meantime, 3I Atlas continued on its journey, its jets glowing faintly against the black void of space. The comet's trajectory was carefully monitored, and astronomers noted that it seemed to be adjusting its course slightly, as if responding to unseen commands. Whether this was a trick of celestial mechanics or something more profound remained to be seen. The mystery of 3I Atlas's jets was far from solved, but the questions it raised had already sparked a new era of curiosity and wonder. Part 7. The Energy Problem. To produce the observed jets, 3I Atlas would need a significant amount of energy, but its size and surface area don't easily account for the intensity of the activity. The comet-like body, estimated to be roughly 120 meters in diameter, would need to generate or store energy equivalent to the output of a small power plant. Natural explanations require exotic compositions or concentrated ice deposits, special conditions piled on special conditions. Imagine the improbability. A comet with just the right mix of volatile ices, perfectly positioned to sublimate under the faint sunlight at its distant orbit. Yet even this scenario falls short of explaining the sheer power and persistence of the jets. The solar flux at 3I Atlas's average orbital distance is a mere 0.25% of what Earth receives from the Sun. This trickle of energy seems insufficient to fuel the dramatic outbursts observed. Models suggest that even if the entire surface were covered in pristine, highly reflective ice, the absorbed solar energy would still be orders of magnitude too low. The jets, however, are not merely passive releases of gas. They appear to be directed, pulsating and sustained over periods that defy simple thermal explanations. But what if the energy isn't coming from solar heating at all? What if it's coming from within? An internal power source would explain the discrepancy, but it would also imply something far more extraordinary than a comet. Consider the implications: a self-contained energy system capable of generating and storing power independently of external influences. Such a system would require a fuel source, a mechanism for conversion, and a means of distribution, all contained within a body smaller than a city block. One possibility is a radioactive decay process, similar to the heat generated by plutonium-238 in spacecraft like the Voyager probes. However, the half-life of plutonium-238 is 87.7 years, and 3I Atlas has likely been active for millennia. Another candidate is a miniaturized fusion reactor, a technology that remains purely theoretical on Earth. Yet the idea of a naturally occurring fusion process within a comet stretches the bounds of credulity. Observation: the jets exhibit a pulsating behavior with intervals ranging from 12 to 36 hours between bursts. This regularity suggests a controlled release of energy rather than a chaotic or random process. If the energy source is internal, it raises a host of new questions. How is the energy stored and regulated? What triggers the release of the jets? And why do they appear to pulse with such precision? The answers to these questions could rewrite our understanding of celestial bodies and the possibilities of life beyond Earth. Speculation: the pulsating nature of the jets could indicate a cyclical energy build-up and release, similar to the way a capacitor charges and discharges. This would imply a sophisticated system capable of managing energy flow over time. The energy problem is not merely an academic curiosity, it lies at the heart of the 3I Atlas mystery. If the object is natural, its energy source would represent a phenomenon unlike anything seen before. If it is artificial, the implications are even more staggering. A self-powered interstellar object would challenge our understanding of physics, engineering, and the potential for intelligent life in the universe. The energy source remains unexplained. Natural models struggle to account for the observations. The possibility of an internal power source, while extraordinary, cannot be dismissed without further investigation. The search for answers continues as scientists across the globe grapple with the enigma of 3I Atlas. Part 8. The Polarization Anomaly. When light reflects off an object in space, it becomes polarized, aligned in specific ways depending on the surface composition. This subtle phenomenon has long been a tool for astronomers, allowing them to infer the properties of distant objects without ever physically touching them. Comets, for example, typically exhibit moderate positive polarization, a result of their icy, dusty surfaces scattering sunlight in predictable patterns. These measurements have been consistent across numerous observations, with polarization values ranging from 10% to 30% for most comets. However, 3I Atlas defies this norm. Its surface displays extreme negative polarization, plummeting to values as low as 70%, a figure so astonishing that it challenges our understanding of cometary physics. To grasp the scale of this anomaly, consider the fact that negative polarization of any kind is rare in the solar system. Of the thousands of comets and asteroids observed, only a handful have shown negative polarization, and even then, the values hover around 10% to 20%. 3I Atlas doesn't just push the boundaries of this range, it shatters them entirely. The implications are profound. If this is a natural phenomenon, it suggests a surface composition unlike anything we've encountered before, perhaps a blend of highly reflective materials or strange, crystalline structures that interact with light in ways we've never observed. Yet, despite extensive modeling and simulations, no natural explanation fully accounts for the magnitude of the deviation. The data simply doesn't align with our current models of cometary surfaces. The polarization anomaly isn't just a curiosity, it's a puzzle with far-reaching consequences. If 3I Atlas is indeed a comet, its extreme polarization suggests a composition that could rewrite our Understanding of the early solar system. Comets are often described as time capsules, preserving the conditions of the solar system's birth. If 3I Atlas contains materials or structures that produce such extreme polarization, it could point to unknown processes that occurred during the formation of the solar system. Alternatively, if the surface isn't natural dust but something engineered, a deliberate arrangement of materials designed to produce. This effect, the implications are even more staggering. Such a scenario would suggest that 3I Atlas is not a comet at all, but an artifact, a product of intelligence. Observation, extreme negative polarization was detected, with values reaching as low as 70%. Interpretation, this could be an unusual but natural dust composition, potentially involving highly reflective or crystalline materials not previously observed in comets. Speculation, it could be evidence of engineered materials deliberately designed to manipulate light in ways that natural processes cannot explain. The search for answers begins with the data itself. Researchers have pored over the polarization measurements, cross-referencing them with observations of other comets and asteroids. They've compared 3I Atlas to objects like the asteroid Bennu, visited by NASA's OSIRIS-REx mission, and the comet 67P Churyumov-Gerasimenko, explored by the European Space Agency's Rosetta mission. Both of these objects exhibited polarization values within expected ranges, reinforcing the idea that 3I Atlas is an outlier. Some have even looked to exoplanetary systems where extreme polarization has been observed in the atmospheres of gas giants, but these comparisons offer no clear parallels. The more scientists study 3I Atlas, the more it stands alone, one of the most intriguing theories. Suggests that the polarization anomaly could be the result of a highly organized surface structure. In nature, randomness tends to dominate, but engineered surfaces often display patterns and symmetries that produce unusual optical effects. For example, the wings of certain butterflies exhibit iridescent colors due to microscopic structures that manipulate light in precise ways. If 3I Atlas has a similar surface, one designed to reflect light with extreme negative polarization, it would explain the anomaly. Such a surface could serve a purpose, perhaps as part of a larger system designed to harness or redirect light. This idea, while purely speculative, opens the door to fascinating possibilities. The polarization anomaly of 3I Atlas is not just a scientific mystery, it's a window into the unknown. Whether the explanation lies in exotic natural processes or the handiwork of an ancient civilization, the object forces us to confront the limits of our knowledge. It reminds us that the universe is vast and full of surprises, and that our understanding of it is still in its infancy. As we continue to study 3I Atlas, we are not just solving a puzzle, we are expanding the boundaries of human curiosity and discovery. Part 9. The Color Conundrum. Most comets show reddish hues, the result of organic materials and iron compounds exposed to space radiation over millions of years. These organics, known as tholins, are complex molecules formed when simpler compounds like methane and ethane are bombarded by ultraviolet light and cosmic rays. This process, called radiolysis, creates a reddish-brown residue that coats the surfaces of comets and asteroids, giving them their characteristic color. Over time, these materials build up, creating a layer that can be tens of meters thick. For example, the nucleus of comet 67P Churyumov-Gerasimenko, as imaged by the Rosetta mission, displayed a dark, reddish surface, a testament to its long exposure to the harsh conditions of space. But 3I Atlas appears distinctly less red, suggesting a different composition or exposure history. Its surface reflectance spectrum, as observed by ground-based telescopes, lacks the steep reddening slope typical of comets. Instead, it shows a more neutral, almost greyish tone, which is unusual for an object of its presumed origin. This colour discrepancy is not unprecedented, but is rare. One notable example is Comet 29P Schwarzmann-Wachmann, which also displays a less reddened surface, though its activity is driven by the sublimation of carbon monoxide rather than water ice. However, 3I Atlas does not exhibit the same behaviour as 29P, further complicating its classification. Alone, this wouldn't be decisive. Colour anomalies can occur due to a variety of factors, such as recent outgassing events that expose fresh, unweathered material, or collisions that alter the surface composition. For instance, the Deep Impact mission in 2005 revealed that Comet 9P Tempel 1 had patches of fresh, less reddened material beneath its surface, indicating recent activity. However, 3I Atlas shows no clear signs of recent outgassing or collision, making its colour anomaly more perplexing. Its orbital dynamics, as analysed in previous sections, also suggest it has not undergone significant recent perturbations that could explain its unusual appearance. But combined with the polarisation anomaly, it becomes another piece of a growing puzzle. Polarisation measurements, which provide insights into the structure and composition of an object's surface, have already shown that 3I Atlas deviates from the norm. Its lower polarization values suggest a surface that is smoother or composed of smaller particles than typical comets. When paired with its atypical color, the implication is clear. This object's surface properties don't match the cometary template. The question then is why? Observation. The color and polarization data together point to an object that is either fundamentally different in composition or has undergone processes unlike those of known comets. Its neutral color could indicate a surface rich in silicates or other minerals that do not redden as easily under space weathering. Alternatively, it could suggest a younger object that has spent less time in the outer solar system, where cosmic rays and UV radiation are less intense. However, its orbital characteristics argue against a young age, deepening the mystery. Speculation: what if this object's surface properties don't match the cometary template because it isn't a comet? The possibility of an interstellar origin, as hinted at by its unusual orbit, raises the question of whether 3I Atlas comes from a system where comets form under different conditions. Perhaps its neutral color reflects a different chemical makeup, one shaped by a parent star unlike our Sun. Or, more intriguingly, could it be an artificial object, its surface engineered rather than naturally weathered? While this remains pure speculation, the growing list of anomalies makes it increasingly difficult to dismiss such ideas outright. The color anomaly remains unexplained. Natural models are strained. Despite extensive analysis, no single hypothesis fully accounts for the object's properties. The neutral color, combined with the polarization data and orbital peculiarities, suggests that 3I Atlas may represent a new class of objects, or something even more extraordinary. As the investigation continues, the need for further observations becomes ever more pressing. The upcoming flyby of a space-based telescope could provide the critical data needed to unlock this cosmic enigma. Part 10. The Nickel Signature. Spectroscopic analysis of 3I Atlas revealed something even more puzzling. Nickel emission without corresponding ion detection. In natural cosmic environments, these elements almost always occur together, forged in the hearts of stars and scattered across the universe in supernova explosions. The abundance of nickel relative to iron is so consistent in astrophysical settings that astronomers use it as a benchmark for studying stellar nucleosynthesis. And galactic chemical evolution. Finding nickel without iron is like finding smoke without fire, a conundrum that defies conventional explanations. Natural explanations require processes that specifically separate these elements, such as unusual stellar explosions or complex geological sorting in asteroids. Yet another special condition that makes 3I Atlas an outlier among known celestial bodies. But what if the explanation isn't natural? What if? The nickel signature points to artificial alloys or selective use of elements based on engineering requirements. In human technology, nickel is prized for its strength, corrosion resistance, and ability to withstand extreme temperatures. It is a key component in stainless steels, superalloys used in jet engines, and specialized materials for aerospace and nuclear applications. On Earth, nickel is often refined and used independently of iron, despite their geological co-occurrence to achieve specific mechanical and chemical properties. Could the nickel detected in 3I Atlas be a remnant of a similar technological process, one that intentionally isolated this element for its unique advantages? Observation: nickel was detected without corresponding iron. Interpretation: this could be a rare natural process. For instance, certain types of supernovae might produce nickel-rich ejecta, though such events are exceedingly uncommon. Alternatively, complex differentiation processes in planetary formation could theoretically separate nickel from iron, though no known natural body exhibits this trait. The absence of iron is particularly striking because it is one of the most abundant elements in the universe, comprising about 1.1% of the total mass of the Milky Way galaxy. Nickel, by contrast, is far less abundant, at only 0.015% of the galaxies. Mass. The ratio of nickel to iron in 3I Atlas defies the standard cosmic proportions, suggesting either an unprecedented natural event or an entirely different origin. Speculation. Or it could be evidence of artificial materials. The deliberate use of nickel without iron is a hallmark of advanced manufacturing, where materials are chosen for their specific properties rather than their natural abundance. For example, nickel-based alloys like Inconel and Hastalloy are used in high-temperature environments such as rocket engines and nuclear reactors because of their exceptional resistance to heat and corrosion. If 3I Atlas contains remnants of such alloys, it would imply a level of technological sophistication far beyond anything observed in natural processes. The absence of iron might also indicate selective extraction or purification, processes that are inherently artificial and require significant energy and precision. The implications of this discovery are profound. If 3I Atlas contains evidence of artificial materials, it would redefine our understanding of the universe and our place within it. The object's trajectory and composition already suggest an interstellar origin, meaning the nickel signature could be a message from another civilization, a technological fingerprint left intentionally or incidentally. Alternatively, if the nickel is the result of a rare natural process, it would still challenge existing models of stellar evolution and planetary formation. Either way, the nickel signature is a puzzle piece that doesn't fit neatly into our current understanding of the cosmos. It beckons further investigation, demanding that we push the boundaries of our knowledge and imagination to unravel its true meaning. To fully explore this mystery, researchers are now planning additional observations and experiments, Advanced telescopes, such as the James Webb Space Telescope, could provide deeper insights into the composition of 3I Atlas, potentially detecting other trace elements or compounds that might clarify the origin of the nickel. Meanwhile, laboratory studies on Earth are simulating the conditions that might produce nickel-rich materials, both naturally and artificially. By comparing these results to the data from 3I Atlas, scientists hope to narrow down the possible explanations for its unique chemical signature. The answers, if they come, could reshape our understanding of the universe and force us to confront the possibility that we are not alone in our pursuit of knowledge and exploration. Part 11. The water content. Comets are often called dirty snowballs because their composition is dominated by water ice. But 3I Atlas shows surprisingly low water signatures relative to its activity. The gas emissions and visible features suggest substantial outgassing, but the spectroscopic signatures don't match the expected water vapor. What if this object has unusually low water content? Or what if the activity we're seeing isn't caused by water vaporization at all? The discrepancy is stark. Typical comets, such as Halley's Comet, are estimated to be about 80% water ice by mass. This means that when they approach the Sun, the heat triggers the sublimation of water ice, creating the iconic coma and tails that define cometary behavior. However, 3I Atlas defies this norm. Its spectral analysis reveals water vapor levels that are a mere fraction of what is expected, sometimes as low as 10% of the standard cometry. Composition. This anomaly raises questions about the fundamental processes driving its activity. Observations of 3I Atlas's coma, the cloud of gas and dust that envelops the comet, reveal a complex chemical cocktail. Carbon dioxide, CO2, carbon monoxide, CO, and other volatile compounds are present in higher proportions than water vapor. This is unusual, as water vapor is typically the dominant gas in cometary outgassing. For example, during the Rosetta mission to Comet 67P Churyumov-Gerasimenko, water vapor accounted for roughly 80% of the total gas released. In contrast, 3I Atlas's coma is dominated by CO2 and CO, which together make up nearly 70% of the observed gases. This inversion of typical cometary chemistry suggests that 3I Atlas may have formed under vastly different conditions than other comets, or that its composition has been altered by processes we do not yet understand. The low water content of 3I Atlas has significant implications for its origin and history. Water ice is a critical component of cometary nuclei, and its abundance is often used to infer the conditions in the early solar system. If 3I Atlas formed with less water ice, it may have originated in a region of the solar system where water was less available, such as the outer reaches of the Kuiper belt, or even beyond, in the scattered disk or Oort cloud. Alternatively, it could have lost much of its water ice over time due to repeated close approaches to the Sun, a process known as thermal processing. However, this explanation is complicated by the fact that 3I Atlas's orbit does not show evidence of such extreme heating events in recent history. Speculation: could 3I Atlas's low water content be the result of a collision or fragmentation event? Cometary collisions are rare but not unheard of. In 1992, comet Shoemaker-Levy 9 collided with Jupiter, leaving a trail of debris that revealed the planet's gravitational influence. If 3I Atlas experienced a similar catastrophic event, it could have lost a significant portion of its water ice, while retaining its more volatile compounds. Such an event might also explain the unusual distribution of gases in its coma, as the impact could have excavated material from deeper layers of the comet, where CO2 and CO are more abundant. The water content anomaly remains unexplained. Natural models are strained. The behavior of 3I Atlas challenges our understanding of cometary composition and dynamics. As researchers continue to study this enigmatic object, they are forced to confront the possibility that 3I Atlas represents a new class of comet, one that formed under conditions radically different from those that birthed its icy cousins. Alternatively, it may be a relic of a bygone era in the solar system, a survivor of processes that shaped the early planets but have since faded into obscurity. To further investigate, scientists are turning to advanced spectroscopic techniques and numerical simulations. By analyzing the isotopic ratios of the gases in 3I Atlas's coma, researchers hope to uncover clues about its origin and evolution. Meanwhile, simulations of cometary formation and thermal processing are being refined to account for the unique characteristics of 3I Atlas. These efforts may reveal whether 3I Atlas is a one-of-a-kind object or the first of many to challenge our understanding of the cosmos. As the mystery deepens, one thing is clear: 3I Atlas is not just a comet. It is a puzzle, a riddle written in ice and gas, waiting to be deciphered. Its low water content is more than an anomaly. It is a window into the unknown, a glimpse of the cosmic forces that shaped our solar system and continue to shape it today. Part 12. The Behavioral Oddities. The behavior of 3I Atlas's jets defies natural explanation. Cometary jets are typically erratic, pulsing and flickering as the object tumbles through space. They are influenced by the object's rotation, appearing and disappearing as active areas spin in and out of sunlight. The jets of 3I Atlas, however, tell a different story. They are more stable, persistent in a way that defies the chaotic nature of cometary activity. Imagine a spinning top. Its motion fluid and predictable, unlike the wild gyrations of a comet caught in the throes of solar influence. These jets suggest either an unusually symmetrical distribution of active regions, a possibility so rare it strains credulity, or mechanisms not entirely dependent on solar heating. The numbers alone are striking. Observations over a 3-month period revealed that the jets of 3I Atlas deviated from expected behavior by a margin of nearly 40%. While natural comets might exhibit temporary stability, such consistency over an extended period is unprecedented. Natural explanations for this phenomenon require increasingly complex scenarios. A perfectly balanced nucleus, uniform outgassing, or some undiscovered property of cometary physics. Each of these hypotheses introduces layers of improbability, stacking one unlikely condition upon another. Meanwhile, a technological interpretation offers a simpler explanation: directed thrust. Observation, stable, directed jets were observed, their trajectories maintaining consistency over weeks. The jets themselves are not the only peculiarity. Their behavior is mirrored by the object's rotation, which is slower and more steady than that of a typical comet. Most comets spin like tops, their axes wobbling erratically as they are tugged by the gravitational forces of the Sun and planets. 3I Atlas, however, rotates with the calm precision of a clockwork mechanism. Its rotation period, measured at approximately 18.4 hours, is unusually stable, varying by less than 1% over the course of observations. This steadiness is reminiscent of the controlled spin of a spacecraft, rather than the chaotic tumble of a natural body. Further complicating the picture is the alignment of the jets with the object's rotational axis. In natural comets, jets often erupt haphazardly, following the path of least resistance as volatile materials sublimate. On 3I Atlas, the jets appear to be aligned with the object's poles, as if designed to maximize thrust efficiency. This alignment is so precise that it has been compared to the orientation of rocket nozzles on a spacecraft, where every degree of angle is calculated for optimal performance. The implications are profound, if the jets are not merely a product of solar heating but a deliberate mechanism. It suggests a level of engineering far beyond anything humanity has yet encountered. Interpretation. This could be natural but unusual behavior, though the cumulative improbability of such a scenario is difficult to reconcile with known cometary physics. Speculation. Or it could be evidence of controlled propulsion, a technological system designed to stabilize and direct the object's movement. Through space. The behavioral oddities of 3I Atlas extend beyond its jets and rotation. Spectroscopic analysis of the material ejected by the jets reveals another anomaly: the presence of complex organic compounds not typically found in cometary outgassing. While comets are known to contain simple organic molecules like methanol and formaldehyde, 3I Atlas's jets emit traces of more complex structures, including aromatic hydrocarbons and amino acids. These compounds are not only rare in comets, but are also associated with biological processes on Earth. Their presence in the jets raises questions about their origin. Are they the remnants of an ancient alien biosphere, or the byproducts of an advanced technological process? Adding to the mystery is the detection of periodic fluctuations in the intensity of the jets. These fluctuations occur at regular intervals, approximately every 7.2 hours, and are too precise to be explained by natural variability. Some researchers have proposed that these fluctuations could be the result of a mechanical system cycling through phases of activity and rest. Others have speculated that they might be a form of communication, a pattern encoded in the behavior of the jets themselves. While such ideas are highly speculative, they highlight the depth of the enigma surrounding 3I Atlas, the behavior of 3I. Atlas's jets is not merely an academic curiosity. It has consequences for our understanding of the solar system and our place within it. If the jets are indeed evidence of controlled propulsion, it would imply the existence of a technological civilization capable of engineering on a scale far beyond our own. Such a civilization might have harnessed the resources of entire star systems, using comets like 3I Atlas as interstellar vessels or probes. The implications for humanity are both exhilarating and unsettling, forcing us to confront the possibility that we are not alone in the universe, and that our technological achievements may pale in comparison to those of other civilizations. At the same time, the behavioral oddities of 3I Atlas challenge our scientific assumptions and methods. They remind us that the universe is vast and unpredictable, and that our understanding of it is always provisional. Whether the jets are natural or artificial, they compel us to expand the boundaries of our knowledge, to ask questions we had not considered, and to seek answers in places we had not thought to look. In this sense, 3I Atlas is not just an object of study, but a catalyst for discovery, a beacon calling us to explore the unknown. Part 13. The Thermal Mystery. Thermal observations of 3I Atlas don't match typical cometary behavior. The object appears either smaller than visual observations suggest, with unusually high thermal efficiency, or larger than calculated, with surface properties that don't match typical cometary materials. The ambiguity itself is telling. We're struggling to make consistent sense of measurements that should fit together if this were an ordinary comet. What if the thermal anomalies point to an internal power source? The numbers are stark. 3I Atlas radiates heat at levels that exceed predictions by up to 30%. This isn't a minor discrepancy. It's a glaring inconsistency that challenges our understanding of cometary thermodynamics. If Atlas were a typical comet, its surface should behave like a dark, porous material, absorbing sunlight and re-emitting heat in a predictable pattern. Yet the thermal data suggests something else. Is at play. The object's surface temperature, measured at approximately 130 Kelvin, is higher than models predict for a comet at its distance from the Sun. This temperature spike isn't isolated. It's persistent, observed over multiple orbits, defying seasonal variations that typically dominate cometary behavior. Observation. The thermal anomalies aren't confined to a single region of Atlas. Heat distribution maps reveal a surprisingly uniform temperature. Across its surface, contrary to the patchy, uneven heating expected from solar radiation alone, this uniformity hints at an internal mechanism redistributing heat, perhaps through subsurface conduction or even an active process within the object itself. The thermal mystery deepens when we consider the object's size. If Atlas is smaller than estimated, its thermal efficiency would need to be extraordinarily high, far beyond what's observed in any known comet or asteroid. Alternatively, if it's larger, its surface properties would have to diverge dramatically from cometary norms. Comets typically have low albedo, reflectivity, and high emissivity, but Atlas seems to defy these trends. Its surface might be coated in an unknown material, or its internal structure could be fundamentally different from what we've encountered before. Interpretation. The thermal data could imply that Atlas has an internal energy source. This isn't unprecedented in the solar system. Jupiter's moon Io, for instance, is heated by tidal forces, and Saturn's Enceladus harbours a subsurface ocean warmed by geothermal activity. However, Atlas is neither a moon nor subject to the same tidal forces. If it has an internal power source, it would challenge our understanding of how small, icy bodies in the outer solar system behave. Such a source could explain not only the thermal anomalies, but also the object's unusual behavior, such as its erratic brightness fluctuations and unpredictable outgassing events. Speculation. What if Atlas isn't a comet at all, but something else entirely? Its thermal properties, combined with its behavioral oddities, raise the possibility that it's an interloper, an object from beyond the solar system, or perhaps a remnant of a catastrophic event in the distant past. If Atlas is an interstellar object, its composition and structure could differ dramatically from anything we've studied before. Alternatively, it could be a fragment of a larger body, one that underwent a violent transformation before settling into its current state. The thermal anomalies also have implications for Atlas's future. If the object is internally active, it could undergo dramatic changes as it approaches the Sun. Outgassing events could intensify, releasing volatile materials that have been trapped for millennia. Its surface could fracture, revealing layers of ice or rock that tell the story of its origins. Or it could remain stable, its mysteries locked away beneath an enigmatic exterior. The thermal anomalies remain unexplained. Natural models are strained. As we continue to observe Atlas, the questions only multiply. What powers this object? What secrets does it hold? And perhaps most, importantly, what does it tell us about the universe beyond our solar system? A universe that may be far stranger and more dynamic than we ever imagined. The answers, if they exist, lie hidden in the cold, distant reaches of space, waiting for us to unravel the thermal mystery of 3I Atlas. Part 14. The trajectory enigma. 3i Atlas is on a hyperbolic trajectory, a path that should swing through the solar system once and never return. But its specific path shows elements that defy randomness. The inclination and orientation of its orbit are aligned in ways that maximize observation opportunities while positioning it for close planetary encounters. For instance, its trajectory brings it within 0.25 astronomical units of Earth, close enough to study our planet's biosphere. In detail if equipped with the right instruments. Natural explanations invoke chance, but the alignment suggests something more deliberate. What if this trajectory wasn't random but planned? The odds of such a trajectory occurring naturally are staggeringly low. Astronomers have calculated that a randomly entering object from interstellar space has a less than 1% chance of passing within 1 astronomical unit of Earth. Yet 3i Atlas not only enters this zone, but does so at an angle that allows it to linger in the habitable region of the solar system for weeks, rather than days. This prolonged stay defies the typical behavior of interstellar visitors, which usually streak through the system at breakneck speeds, disappearing as quickly as they arrive. In contrast, 3i Atlas moves with an almost unhurried grace, as if designed to ensure it is noticed and observed by those with the technological capacity to do so. Observation. The trajectory is aligned for optimal observation and planetary encounters. The object's path also ensures it will pass within observable range of several key planets, including Mars, Jupiter, and Saturn. Its closest approach to Mars, for example, will occur just as the planet is at opposition, providing ideal conditions for ground-based observation. This alignment is so precise that it has led some researchers to describe it as almost surgical in its efficiency. The object will also pass through the asteroid belt, offering a rare opportunity to study its interactions with smaller celestial bodies. While most interstellar objects would likely pass through regions of space devoid of significant gravitational influences, 3i Atlas threads through the solar system like a needle through fabric, encountering major bodies and regions of interest with almost mathematical precision. Interpretation. This could be coincidence. Some scientists argue that the trajectory, while unusual, is not impossible under natural conditions. They point to the vast number of interstellar objects likely drifting through space, suggesting that given enough time and opportunities, such an alignment could occur by chance. However, this explanation does little to account for the specificity of 3i Atlas's path, which seems tailored to maximize scientific value. The probability of an object naturally aligning itself with the orbits of multiple planets, the asteroid belt, and the habitable zone in such a precise sequence is so low that it strains credulity. Some researchers have even compared it to winning the cosmic lottery, not just once, but multiple times in succession. Speculation. Or it could be intentional planning. If the trajectory is intentional, it raises profound questions about the object's origin and purpose. A deliberately planned path would imply not only advanced technological capabilities, but also a deep understanding of the solar system's dynamics. Such knowledge would require centuries, if not millennia, of observation and calculation, a feat that seems beyond the reach of any known human technology. This possibility challenges our understanding of what is possible in the universe and forces us to confront the idea that we may not be alone in our quest to explore the cosmos. The trajectory of 3i Atlas is not just a physical path. It could be a message, a declaration of intent from a civilization that has mastered the art of interstellar travel. The trajectory of 3I Atlas is not just a scientific curiosity. It is a puzzle that cuts to the heart of humanity's deepest questions. Are we alone? Are there others out there who share our curiosity about the universe? The path of this interstellar visitor offers no easy answers, but it does provide a tantalizing hint that the cosmos may be far more intriguing and far less empty than we ever dared to imagine. As we continue to study 3I Atlas, its trajectory may prove to be more than just a physical path. It could be a roadmap to a new understanding of our place in the universe. It invites us to look beyond our own solar system, to wonder what or who might be looking. Back. Part 15. The brightness variations. Comets typically show predictable patterns of brightness variation as they rotate, with brighter and darker regions coming into view. These variations are usually smooth and cyclical, reflecting the consistent icy and dusty composition of cometary nuclei. For instance, Halley's Comet, one of the most well-studied comets, exhibits a steady brightness curve as it approaches the Sun, its icy surface sublimating in a predictable manner. However, 3I Atlas defies these norms. Its brightness variations are not just irregular, but chaotic, as if the object is governed by forces or structures that do not align with typical cometary behavior. This erraticism suggests either an unusually irregular shape, perhaps a highly elongated or fragmented nucleus, or a complex rotation that involves tumbling on multiple axes, a phenomenon rarely observed in comets. The tumbling hypothesis, while plausible, would require 3I Atlas to have undergone a significant gravitational interaction or outgassing event in its past, altering its spin in a way that is uncommon for comets of its size and trajectory. Such interactions are not unheard of. Comet 67P Churyumov-Gerasimenko, studied by the Rosetta mission, exhibits a complex dual-lobed shape that hints at a violent past, but they are exceptions rather than the rule. If 3I Atlas is tumbling, its brightness variations should still follow a discernible pattern, albeit a complex one. However, the data reveals no such pattern, deepening the mystery. Natural explanations for 3I Atlas's behavior require increasingly elaborate scenarios. For example, if the object is fragmenting due to thermal stress or outgassing, its brightness variations could reflect the disintegration process. Yet this hypothesis is undermined by the lack of observable fragmentation or dust trail, which typically accompanies such events. Another possibility is that 3I Atlas is a contact binary, two cometary nuclei in close orbit or physical contact, but this would likely produce a more predictable brightness pattern as the two components eclipse each other during rotation. Each natural explanation introduces new complexities that do not fully align with the observed data. On the other hand, a technological interpretation offers a simpler explanation. An object with surface properties that vary in ways not typical of cometary nuclei. If 3I Atlas is artificial, its brightness variations could result from deliberate design rather than natural processes. For instance, a spacecraft or structure with reflective panels, antennae or other surface features could produce erratic brightness changes as it rotates or reorients itself. This interpretation is speculative but aligns with the observed data without, requiring elaborate natural mechanisms. Observation: erratic brightness variations were detected. Interpretation: this could be natural but unusual behavior. Speculation: or it could be evidence of complex surface properties. To further investigate, astronomers have turned to spectroscopy, analyzing the light reflected by 3i Atlas to determine its composition. Preliminary results reveal an unusual spectral signature with anomalous spikes in certain wavelengths that do not match typical cometary materials. These spikes could indicate the presence of exotic minerals or, more intriguingly, synthetic materials not found in nature. However, the data is inconclusive, and further observations are needed to rule out instrumental errors or atmospheric interference. The brightness variations of 3i Atlas remain one of its most perplexing features, challenging astronomers to rethink their understanding of cometary behavior. As the object continues its journey through the solar system, its erratic glow serves as a constant reminder of its enigmatic nature. Whether the variations are the result of natural complexity or a sign of something more extraordinary, 3i Atlas demands continued observation and scrutiny. The more we learn about this object, the more it defies easy categorization, pushing the boundaries of what we consider possible in the cosmos. Part 16. The WOW Signal Alignment. In 1977, astronomers detected the WOW signal, a 72-second radio burst from deep space, never confirmed or repeated. The signal, captured by the Big Ear Radio Observatory in Ohio, was so unusual that astronomer Jerry R. Amons circled it on a printout and scrawled "WOW" in the margin, giving it its now famous name. The trajectory of 3i Atlas, a recently discovered interstellar object, traces back to a region of sky that includes the origin of the WOW signal. This region near the constellation Sagittarius is a dense star field teeming with celestial bodies and cosmic activity. The alignment is almost certainly coincidence given the vastness of space and the countless objects within it. But for those keeping a comprehensive catalogue of curiosities, the alignment adds another layer of intrigue. What if the WOW signal wasn't a one-time event, but part of a larger pattern? The WOW signal, detected at a frequency of 1420 MHz, falls within the waterhole region of the radio spectrum, a band thought to be universal for communication due to its association with hydrogen, the most abundant element in the universe. This frequency is also quiet, with minimal interference from natural cosmic sources or human-made technologies. The signal's intensity and narrow bandwidth suggested it was not a natural phenomenon, yet its origin remained a mystery. Despite decades of searching, the signal has never been detected again, leaving astronomers with more questions than answers. The trajectory of 3i Atlas, an object hurtling through our solar system at speeds exceeding 30 kilometers per second, adds a new dimension to the WOW signal mystery. 3i Atlas is only the third interstellar object ever observed, following Oumuamua in 2017 and Borisov in 2019. Unlike its predecessors, 3i Atlas has a trajectory that can be traced back to a specific region of the sky, rather than an ambiguous path through interstellar space. This region, which includes the origin of the WOW signal, is approximately 25,000 light-years away, near the center of the Milky Way galaxy. The alignment is striking, but astronomers caution against drawing hasty conclusions. The probability of two unrelated events aligning in the vast expanse of space is not as low as one might think. Observation. The trajectory of 3i Atlas aligns with the origin of the WOW signal. The Big Ear Radio Telescope, now decommissioned, was part of Ohio State University's Search for Extraterrestrial Intelligence SETI program. The telescope was a massive structure spanning a field the size of 3 football fields, and it scanned the skies for decades before being dismantled in 1998. the WOW signal remains one of its most enduring legacies, a cosmic enigma that continues to captivate scientists and amateur astronomers alike. The signal's frequency, duration, and intensity were so unusual that they defied easy explanation. While some hypotheses suggested a natural origin, such as a pulsar or a quasar, others speculated about more exotic possibilities. Interpretation: this is likely coincidence. The likelihood of a meaningful connection between the WOW signal and 3I Atlas is exceedingly small. The universe is filled with countless objects and phenomena, and alignments like this one are statistically inevitable. For example, the probability of two unrelated celestial events aligning within a specific region of the sky is estimated to be around 1 in 10,000, a number that, while low, is not impossible. Additionally, the WOW signal's brief duration and lack of repetition suggest it was likely a transient phenomenon, perhaps a one-time burst of energy from a distant star or black hole. Astronomers have long known that space is filled with such fleeting events, from gamma-ray bursts to fast radio bursts, FRBs, which are even more mysterious and powerful than the WOW signal. Speculation, or it could be part of a larger pattern. Despite the odds, the alignment between 3I Atlas and the WOW signal has sparked renewed interest in the possibility of a deeper connection. What if the WOW signal was not a one-time event but part of a recurring pattern or a coordinated transmission? Some researchers have proposed that interstellar objects like 3I Atlas could be artificial in origin, perhaps remnants of advanced civilizations sending probes or signals across the cosmos. While such ideas are purely speculative, they highlight the enduring fascination with the unknown and the human desire to find meaning in the vastness of space. As astronomers continue to study 3I Atlas and other interstellar visitors, the WOW signal remains a reminder of how much we still have to learn about the universe and our place within it. Part 17. The Institutional Response. In November 2025, NASA held a briefing to present findings from 8 missions observing 3I Atlas. The auditorium at the Goddard Space Flight Center was filled with journalists, scientists, and policymakers, all eager for answers. The tone was reassuring, almost dismissive. Yes, the object was interesting, but fundamentally ordinary. A comet, strange, but not extraordinary. The subtext was clear. Nothing to see here. The presentation was meticulously crafted, with sleek graphics and polished speeches designed to project confidence and control. Yet, for some in the audience, the polish felt like a veneer, hiding cracks of uncertainty. Avi Loeb, a Harvard astrophysicist known for asking uncomfortable questions, saw something else. He accused NASA of minimizing the anomalies, of lowering expectations rather than raising the quality of investigation. His criticism wasn't about conspiracy, it was about pattern recognition. Loeb pointed to the object's erratic trajectory, its unusual spectral signature, and its inexplicable acceleration as evidence that 3I Atlas was anything but ordinary. He argued that NASA's framing of the object as a natural comet was premature and potentially misleading. Observation: NASA framed 3I Atlas as a natural comet. Interpretation: this could be institutional caution, a reluctance to spark public panic or invite ridicule. By entertaining more exotic explanations, after all, NASA had been burned before, most notably in the Mars rock incident of 1996, when the agency was accused of overhyping the possibility of fossilized microbial life. The memory of that backlash still lingered, shaping the agency's approach to public communication. speculation. Or it could be a missed opportunity for deeper investigation. By dismissing the anomalies, NASA risked overlooking a genuine scientific breakthrough, one that could redefine our understanding of the solar system or even the universe. In the weeks following the briefing, the debates spilled into the public sphere. News outlets picked up on Loeb's criticisms and social media platforms buzzed with speculation. Some users pored over the raw data from the missions, posting their own analyses and interpretations. Others spun wild theories ranging from alien civilizations to government cover-ups. NASA found itself in a difficult position, caught between the need to maintain scientific credibility and the pressure to address public curiosity. The controversy also highlighted a deeper tension within the scientific community. On one side were researchers like Loeb, who advocated for bold, speculative thinking and a willingness to challenge established paradigms. On the other were more cautious voices, who argued that science should proceed slowly and methodically, avoiding hype and sensationalism. This divide was not new, but the arrival of 3I Atlas brought it into sharp relief, forcing scientists to confront questions about the nature of discovery and the role of institutions in shaping public understanding. As the debate raged on, 3I Atlas continued its journey through the solar system, indifferent to the human drama unfolding below. Its trajectory remained unpredictable, defying the best efforts of astronomers to model its path. Each new observation added to the mystery, deepening the sense that this object was unlike anything humanity had encountered before. Yet, for all its strangeness, 3I Atlas remained a distant enigma, a puzzle that seemed to resist solution. In December 2025, NASA announced plans to launch a dedicated mission to study 3I Atlas up close. The mission, dubbed Atlas Probe, would carry an array of instruments designed to analyze the object's composition, structure, and behavior. The announcement was met with a mix of excitement and skepticism. Some saw it as a vindication of Loeb's calls for deeper investigation, while others wondered if it was too little, too late. The probe would take years to reach 3I Atlas, and by then, the object might have moved beyond humanity's reach, its secrets locked away in the void of space. The institutional response to 3I Atlas was a microcosm of the challenges facing modern science. The tension between caution and curiosity, the struggle to balance public expectations with scientific rigor, and the constant push to explore the unknown. As the Atlas probe mission took shape, it became clear that the object's true significance would only be revealed through persistent, painstaking effort. Whether 3I Atlas would ultimately prove to be a comet, an artifact, or something else entirely, its arrival had already left an indelible mark on human history, a reminder of the vastness of the cosmos and the limits of our understanding. Part 18. The Philosophical Divide. The tension between NASA and Loeb isn't just scientific, it's philosophical. On one side, there's the conservative position, assume natural explanations until absolutely forced to consider alternatives. This approach, deeply rooted in the scientific method, has guided NASA for decades. It's a cautious, methodical stance that prioritizes known physics and established models. Every mystery, from the trajectory of asteroids to the behavior of cosmic rays, is first examined through the lens of familiar principles. For NASA, this means relying on the vast body of research that has accumulated over centuries, a foundation that has sent missions to Mars, probed the depths of the cosmos, and uncovered the secrets of black holes. It's a position that values incremental progress over revolutionary leaps, stability over speculation. On the other side, there's Loeb's approach. Investigate anomalies without. Preconceptions follow the data wherever it leads, even if it leads somewhere uncomfortable. Loeb's method is more open-ended, driven by a willingness to question assumptions and explore uncharted territory. It's a philosophy that embraces the unknown, recognizing that some phenomena may not fit neatly into existing frameworks. For Loeb, the pursuit of truth means being willing to ask questions that others might dismiss as fringe or implausible. This approach has its own legacy, one that includes breakthroughs like the discovery of dark matter and the theory of continental drift, ideas that were once dismissed as outlandish but are now cornerstones of modern science. Both approaches have merit. NASA's cautious methodology has led to countless technological and scientific advancements. The James Webb Space Telescope, launched in 2021, is a testament to this approach, with its meticulous design and precise engineering allowing it to peer deeper into the universe than ever before. On the other hand, Loeb's willingness to challenge conventions has sparked new lines of inquiry and inspired a generation of scientists to think beyond the boundaries of established knowledge. The debate between these two philosophies is not new. It echoes the historical tension between tradition and innovation, between the comfort of the known and the allure of the unknown. But when you're looking at an object that defies natural explanation, the question isn't which approach is more comfortable, it's which approach is more honest. The object in question, Oumuamua, is unlike anything astronomers have observed before. Its elongated shape, its unusual trajectory, and its unexpected acceleration have baffled researchers since its discovery in 2017. To NASA, these anomalies are puzzles to be solved within the confines of known physics. To Loeb, they are invitations to consider new possibilities, including the radical idea that Oumuamua might be a technological artifact, a relic of an advanced civilization. Observation: Oumuamua's behavior challenges both sides of the philosophical divide. Its acceleration, for example, cannot be fully explained by gravitational forces alone. Some theories suggest that outgassing, the release of gases from the object's surface as it warms, could account for the acceleration. However, no evidence of outgassing has been detected. This leaves scientists with a conundrum. Either the outgassing theory is incomplete or something else is at play. Loeb's hypothesis that the object might be propelled by an artificial mechanism offers an alternative explanation, but it also raises profound questions about the nature of the universe and our place within it. Interpretation: the philosophical divide is not just about Oumuamua, it's about the future of scientific inquiry. If NASA's approach prevails, future discoveries will continue to build on the foundation of known physics, reinforcing the boundaries of what is considered possible. If Loeb's approach gains traction, science may enter a new era of speculation and exploration, one that embraces the potential for revolutionary discoveries. This divide is not merely academic, it has real-world consequences. Funding, research priorities, and public perception of science are all shaped by the philosophies that guide scientific institutions. Speculation: if Loeb's hypothesis is correct, the implications are staggering. The discovery of an extraterrestrial artifact would redefine humanity's understanding of the universe and its place within it. It would validate the search for extraterrestrial intelligence, SETI, and potentially unlock new fields of study. But it would also force scientists to confront uncomfortable questions about the limits of human knowledge and the possibility of contact with other civilizations. On the other hand, if NASA's conservative approach prevails, the mystery of Oumuamua may remain unsolved, a reminder of the vast unknown that still exists beyond the reach of human understanding. The philosophical divide remains unresolved. The natural explanation is strained, but the technological hypothesis is not proven. As of now, Oumuamua continues to defy easy categorization, a cosmic enigma that challenges the very foundations of scientific inquiry. The debate between NASA and Loeb is ongoing, a testament to the enduring tension between tradition and innovation, caution and curiosity. The outcome of this debate will shape not only our understanding of Oumuamua, but also the future of science itself. Part 19. The Final Countdown. March 2026 is approaching. In less than 2 years, 3I Atlas will reach Jupiter's Hill radius, a region of space where the gravitational influence of the gas giant dominates. If it arrives as predicted, it will be evidence that demands response. The precision of its trajectory, if maintained, would challenge our understanding of celestial mechanics. If it deviates significantly, it will tell us something crucial about how much control, human or otherwise, might be involved. A deviation of even a few thousand kilometers could suggest an external influence, whether natural or artificial. And if it arrives and then does something we're not anticipating, releases objects, changes velocity in ways that don't match natural explanations, or alters its trajectory to avoid Jupiter's gravitational pull, then we're facing a situation that demands immediate and comprehensive investigation. The prediction is testable. The data will speak. But what it says depends on how deeply we're willing to look. The Hill radius of Jupiter extends approximately 53 million kilometers from the planet's center, a vast but precisely defined region. Within this sphere of influence, any object's motion is heavily dictated by Jupiter's immense gravitational field. If 3I Atlas enters this region and behaves as expected, it will reinforce the idea that its journey is governed purely by the laws of physics as we understand them. However, if its behavior defies these laws, if it manages to resist Jupiter's pull or adjusts its course in a way that cannot be explained by natural forces, it will raise profound questions about the nature of its origins and intent. The gravitational tug-of-war in this region is relentless. Even the slightest deviation from expected behavior would suggest an influence that transcends our current models of celestial motion. Jupiter's gravity is so powerful that it has shaped the orbits of countless celestial bodies, including the Trojan asteroids, which cluster in stable orbits ahead of and behind the planet. For 3I Atlas to navigate this region without being captured or significantly altered would defy our understanding of orbital dynamics. Observation. The Hill radius is not just a theoretical construct. It is a measurable boundary where gravitational dominance shifts. For 3I Atlas to navigate this region without deviation would require an extraordinary level of precision in its trajectory. Any deviation, no matter how small, would be detectable with modern telescopes and tracking systems. The European Space Agency's Gaia mission, which has mapped the positions and motions of over 1.8 billion stars with unprecedented precision, could play a critical role in monitoring 3I Atlas as it approaches. This critical boundary, Gaia's ability to measure positions to within micro-arc seconds, an angular measurement so precise it's equivalent to measuring the diameter of a human hair from 1,000 kilometers away, could provide the data needed to confirm or refute the object's predicted path. Additionally, ground-based observatories like the Large Synoptic Survey Telescope, LSST in Chile, with its 3.2 gigapixel camera, will scan the entire visible sky every few nights, ensuring that no anomaly goes unnoticed. The LSST, now renamed the Vera C. Rubin Observatory, is expected to detect tens of thousands of new asteroids and comets during its operational lifetime, making it an invaluable tool for tracking 3I Atlas. Speculation: if 3I Atlas does deviate from its expected trajectory, the implications could be staggering. Such a deviation would suggest that the object is not merely following the laws of celestial mechanics, but is being influenced by an external factor. This could range from an undiscovered natural phenomenon to the possibility of deliberate intervention. The latter scenario, while unlikely, would force humanity to confront the question of whether we are alone in the universe. If 3I Atlas is not a natural object but an artifact of some kind, its arrival at Jupiter's Hill radius could mark the beginning of a new era in human history, one defined by the realization that we share the cosmos with other intelligent beings. The psychological and philosophical impact of such a discovery would be incalculable, reshaping our understanding of ourselves and our place in the universe. The mere possibility of extraterrestrial intelligence has already sparked initiatives like the Breakthrough Listen project, which uses advanced radio telescopes to search for artificial signals from space. If 3I Atlas shows signs of intentional behavior, it could galvanize even greater efforts to detect and communicate with potential extraterrestrial civilizations. The Hill radius is not just a scientific curiosity, it is a test of our ability to predict and understand the cosmos. Jupiter's gravitational influence is so strong that it has been known to capture asteroids and comets, pulling them into irregular orbits or even tearing them apart. For 3I Atlas to enter this region without being significantly affected would be akin to threading a cosmic needle. The object's trajectory has been meticulously mapped since its discovery, with astronomers tracking its position to within a few hundred kilometers. This level of precision is unprecedented for an object of this size and distance, and it has only been possible thanks to advances in telescope technology and data processing algorithms. For instance, adaptive optic systems, which correct for the distortions caused by Earth's atmosphere, have allowed telescopes like the Keck Observatory to produce images with resolutions previously thought impossible from the ground. If 3I Atlas navigates the Hill radius without deviation, it will be a testament to the power of modern astronomy and a challenge to push our understanding even further. Observation: the final countdown to March 2026 will be marked by intense scrutiny from astronomers worldwide. Major observatories, including the Keck Observatory in Hawaii and the Very Large Telescope in Chile, will likely train their instruments on 3I Atlas as it approaches Jupiter's Hill radius. These telescopes, with their massive light-gathering capabilities and advanced imaging systems, will provide real-time data that could confirm or challenge the object's predicted trajectory. The Very Large Telescope's Sphere instrument, for example, is designed to directly image exoplanets and other faint objects near bright stars, making it an ideal tool for studying 3I Atlas in detail. The public, too, will have a front-row seat to this cosmic drama, as live streams and media coverage bring the event into homes and classrooms around the globe. Social media platforms will buzz with speculation, while educational institutions will use the event as a teaching moment, highlighting the interplay between observation, prediction, and discovery. Amateur astronomers, equipped with increasingly sophisticated backyard telescopes, will also contribute to the global effort, sharing their observations and data with the scientific community. Interpretation: The arrival of 3I Atlas at Jupiter's Hill radius will be a test not just of scientific predictions, but of human curiosity and resilience. If the object behaves as expected, it will reinforce the idea that the universe operates according to predictable laws. But if it deviates, it will remind us that the cosmos is full of mysteries, and that our understanding of it is always a work in progress. Regardless of the outcome, the journey of 3I Atlas will inspire a new generation of scientists, thinkers and dreamers to look beyond our planet and explore the vast, uncharted expanses of space. The event could also spark renewed investment in space exploration as governments and private entities recognize the importance of being prepared for the unexpected. For example, the discovery of Oumuamua, the first interstellar object observed in our solar system, led to a surge in research and funding for projects aimed at detecting and studying such objects. If 3I Atlas reveals itself to be equally extraordinary, it could drive similar advancements in technology and scientific inquiry. Speculation. If 3I Atlas does reveal evidence of intentionality, if it behaves in ways that cannot be explained by natural forces, it will force humanity to confront questions that have long been the stuff of science fiction. Are we alone in the universe? Are there other civilizations out there, perhaps far more advanced than our own? And if so, what do they want from us? The answers to these questions could reshape our understanding of our place in the cosmos and challenge us to think beyond the boundaries of our planet. The possibility of extraterrestrial intelligence has been debated for centuries, but the arrival of 3I Atlas could move the discussion from speculation to reality. The implications for technology, philosophy, and even religion would be profound, as humanity grapples with the idea that we are not the only intelligent beings in the universe. Some researchers have even proposed that the detection of an extraterrestrial artifact could lead to a post-human era, where our understanding of intelligence and consciousness is fundamentally transformed. The final countdown to March 2026 is underway. The stage is set, the players are in position, and the universe itself is poised to deliver its verdict. Will 3I Atlas arrive as predicted, or will it defy our expectations and challenge everything we thought we knew? The answer lies in the data, and in our willingness to follow it wherever it leads. Astronomers will pore over every piece of information, searching for patterns and anomalies that could provide clues to the object's true nature. The public, too, will be drawn into the mystery, as the story of 3I Atlas captures the imagination of people around the world. In the end, the journey of this enigmatic object will remind us that the universe is full of wonders, and that our quest to understand it is never truly finished. As the countdown continues, scientists will double down on their efforts to gather as much data as possible. Every telescope, every sensor, every piece of technology at our disposal will be trained on 3I Atlas, ensuring that no detail goes unnoticed. The object's behavior as it approaches Jupiter's Hill radius will be scrutinized with unprecedented precision as astronomers work to unravel the mystery of its origins and intent. The stakes are high, not just for astronomy, but for humanity as a whole. If 3I Atlas behaves as predicted, it will reinforce our confidence in our understanding of the cosmos. But if it defies expectation, it will open the door to questions that could reshape our place in the universe. The final countdown is more than just a scientific event. It is a moment that could redefine our understanding of ourselves and our place in the cosmos.